All right. Well, I'm going to go ahead and get started. Um, Jim has suggested um, a topic, and my idea was uh, to give him the second meeting, although I'm not sure if you want to talk about dark matter or not, first or second. So I can give my presentation first if you would like. Um, it's kind of brief. Did anybody take a look at any of the information I sent out? Um, I think Vladimir did.
I had a
Yes, sir.
quick look at it. There was so much information there. There was Sabine Hossenfelder, and there was,
Yeah.
I glanced at everything, but n not in detail.
Well, Sabine is actually what triggered this. So I'm going to go ahead. I was more interested in her comments about what she thought about this. I was more interested in that than I was in the particular specifics of what they were talking about. But I'm going to go ahead and talk a little bit about the specifics. I haven't done this in a while. Okay, so is it working? Do you see the presentation? Or
Yes, it's just come
So,
up.
okay, so um, this is about this the dark Big Bang, and the paper came out on Archive X about the dark Big Bang, and some of the and Sabine Hossenfelder in her video, which is what I came across first, there was this idea of there are two big bangs. Apparently, the press media got a hold of the two big bangs. So anyway, this is from the abstract of the paper that caused this. In this work, we described a scenario in which dark matter and possibly dark radiation can be formed around or even after BBN in a second Big Bang, which we dub the Dark Big Bang. Wow, what are they talking about? And the second thing, ultra heavy dark matter can originate directly from bubble collisions during the Dark Big Bang. Well, you need to know what the Dark Big Bang is, but this kind of essentially uh, it's this bubble collisions that are happening during this dark Big Bang is their idea of. That's kind of an important thing to what they're talking about. The dark Big Bang gives rise to striking gravity wave signatures to be tested at pulsar timing array experiments. Okay, so what they're talking about is they've come up with this scenario, and um, their scenario is that gravitational waves are going to be created and they can be detected. So this is really important. The two big bangs. Okay. The very early universe went through an epoch of inflation. We talked about inflation, a rapid expansion of space driven by vacuum energy. Not really sure exactly what that means. The origins of matter and radiation lie in the hot Big Bang, which terminates inflation and releases the vacuum energy into a hot plasma of particles. Boy, that's a real mouthful, isn't it? There is no genuine reason for a common origin of visible and dark matter beyond simplicity. Okay, so what they're saying is um, we're gonna have two processes occurring basically in parallel, but not interacting with each other. So there's the creation of visible matter in one physical process and the creation of dark matter in another physical process, and they're occurring side by side. Okay. so that they can separate them, um, and talk about the two things completely separate. That's where the two big bangs come from. And they're saying, we can do that. We have a justification for doing that. Despite excessive experimental searches over decades, no direct non-gravitational interaction between visible and dark matter have been detected. Well, that kind of justifies their separating the dark Big Bang from the Big Bang. This is a direct quote. They're talking about their cosmological scenario in which the visible and the dark matter sector are completely decoupled other than through gravity. The hot Big Bang only includes visible radiation and matter, but no dark matter at all. However, while the dark sector is cold at first, it contains a small amount of vacuum energy, which is initially highly subdominant compared to the radiation density of the universe. Boy, that's a mouthful. Because vacuum energy does not redshift, the dark vacuum contribution can become significant at a later stage of the universe, although it never dominates the energy density of the universe. When the dark vacuum finally decays in a dark phase transition, it can induce significant amounts of dark matter and possibly dark radiation. Wow. Anybody have any questions about that? I certainly have lots of questions.
Well, what type of energy could a vacuum have?
Well, you have to ask them, I guess. I'm not. Anyway, what they're really trying to say, I think, is this is a lot of jargon that really basically says what we have is a theory that says we can explain how dark matter is created at the same time that relative common matter, or matter that we're familiar with which they call visible matter. So these two things can occur in parallel. So the two scenarios are occurring. So you have two Big Bangs. You have a Big Bang that explains the origin of regular matter, or what they call visible matter, which we're familiar with, which used to be what cosmological models explain. And so now we have another separate theory of cosmology, or cosmological model, that explains how dark matter originates. Okay, source of dark matter, they're saying, okay, so this is where the dark matter comes from. Due to the analogy with the hot Big Bang, which transfers the inflationary vacuum energy into visible particles, we call this process the dark Big Bang. So here you got kind of a terminological difficulty. I'm not sure what they mean by this. By inflationary vacuum energy, I think they mean dark energy. And this is kind of where all this terminology gets confused. And anyway, so the next one is specifically, we will introduce a dark sector, not sure what that means, scalar field, which initially populates a metastable minimum in its potential, initiates the dark Big Bang. Bubbles of true vacuum form at random nucleation sites, expand, collide, and produce dark matter and dark radiation. That's a lot of stuff to basically say that what they're hypothesizing is some kind of chaotic process through this concept of creating bubbles, whatever a bubble means. Presumably it's a bubble with nothing in it. It's a vacuum bubble. And the dark matter is created at the boundaries of all these bubbles. And these bubbles are being created and they bounce into each other and create gravitational waves. That's the bottom line. So these bubbles that are being created create gravity waves. Okay, so because the dark matter is this, in their scenario, these bubbles are colliding and there's a lot of turbulence and activity going on. There's going to be gravity waves generated. That's the key point. Besides the dark matter signatures, the dark Big Bang induces significant amounts of gravitational radiation by the collision of true vacuum bubbles during the phase transition. That's a lot of talk, isn't it? Gravitational wave searches by pulsar timing arrays exhibit a striking potential to discover the dark Big Bang phase transition. So what they're saying, in effect, is we kind of discover the existence of dark Big Bang by gravity.
We should have done it the other way, where I set one up for over on that one, but he was convinced he had it working.
Well, I thought he did too.
What he should do is set up not come here, but set up a Zoom.
All
Maybe,
right.
maybe,
Well, on his computer or something.
Maybe.
Either Peter.
yeah.
Popular. Okay. So I guess that was your wife there, Bob.
Yeah. Yeah, it's funny. We thought we had the camera working and it seemed to work. We had someone over here and still doesn't work.
That's
Camera's not working, but the mic was.
Yeah, the mic works, but not the camera. I don't know what's going on.
all right. Okay. So now I'm going to talk a little bit about this is kind of like stuff that I took out of a popular press article. So I sort of gave you what the paper supposedly is talking about, mainly from the abstract and the introduction, which is the only two parts that are really basically this. They're full of jargon, but they try to convey a concept of what we're talking about. Now, the popular press has kind of a different take. What they say is when inflation ended, the exotic quantum fields that drove that event decayed, transforming themselves into the flood of particles and radiation that remain today. Now, this is kind of interesting because I think this is this reporter's idea of how the whole creation process occurs in the Big Bang Theory. Okay. And so the current idea is there's the beginning and then there's energy. So at the T0, energy materializes in the universe. It suddenly appears in the universe. And then an inflation occurs. I'm not sure exactly what that means. And when the inflation ends, that's when the creation of matter starts. And this is called reheating, as I understand it. So what they're saying here is when inflation ended, okay, so inflation ends, the exotic quantum fields that drove that event decayed, transforming themselves into the flood of particles and radiation that remain today. I think this is really the key point about what the Big Bang is saying. This is the key point of the whole theory, of the standard theory that they're talking about. I never really understood this, so this was helpful in understanding how this works. However, despite the success of our picture of the early universe, the first paragraph described that, we still do not understand dark matter, which is the mysterious and invisible form of matter that takes up the vast majority of mass in the cosmos. Wow, it's the vast majority of mass in the cosmos, and we don't understand it. Oh, wow. The standard assumption in Big Bang models is that whatever process generated particles and radiation also created the dark matter. And after that, the dark matter just hung around, ignoring everybody else. That's kind of funny use of metaphor. There was some quantum field remaining that did not decay away. As the universe expanded and cooled, that extra quantum field did eventually transform itself, triggering the formation of dark matter. Okay, so this is, I think they're talking about the standard approach that is being used. The advantage of this approach is that it decouples the evolution of dark matter from normal matter, so that Big Bang nucleosynthesis can proceed as we currently understand it while the dark matter evolves along a separate track. Okay? That's basically a summary of what this idea is supposed to be about. Does anybody have any questions about that?
It's
Sure.
hard to answer the question. Word salad.
Yes, well, it's
Yeah, it's just statements. I mean, you can keep on making these statements,
well,
but
I summarize. I've sort of summarized it really. I just basically took key points and summarized it. Okay, but the real idea is that there has that they're looking for some process that they can explain how dark matter came into being. Okay, and because dark matter has no they've never detected dark matter in any experiment. They have no idea what its properties are, and so you can't. How do you describe something that you don't know what its properties are physically? So it's like stumbling around in the dark. Okay, I'm going to talk a little bit about Sabine Hassenfelder's video here. And she says that the words Big Bang are being misused. And I didn't really quite understand exactly what she meant by saying that. Whether she sort of is trying to say that Big Bang means the origin of time itself at the very start. Okay. And that they're not talking about what happens at the very start. They're talking about what happens after inflation. Okay. And so the inflation field, whatever inflation is, this energy, vacuum energy thing, whatever it is that supposedly exists after the beginning during the period of inflation. And I think that's what they're calling the inflation field. The inflation field at the end of inflation decays to form matter. And that this is called reheating. Interesting. Okay, reheating. What does that mean? It starts heating up when this decay happens. So during inflation, apparently, during inflation, the energy cools off. And then when inflation ends, the universe heats up again. So that's why they're calling it reheating. Okay, then she uses this term called TIM, which apparently means the introduction of matter, which some people thought in the comments that was pretty clear. Since dark matter doesn't interact with matter, there is no way to determine the properties of dark matter. So I talked about that. So in effect, basically, how do we know what dark matter is since it doesn't interact with matter? There is no way to determine the properties of it. So they've never found dark matter in any experiment. And so it's because we've never found dark matter in any experiment, we can't know anything about what its properties are, right? That makes sense, right? Okay. And then she makes this I think is the real point of her video. She puts down a number of principles. These I think, are philosophical principles or science philosophy principles. And the first principle is don't invent an unnecessary theory. Why are you inventing an unnecessary theory? Why are we doing it? So don't do that. Avoid conflict with evidence. Okay, so this is how they're doing it. They avoid conflict with any evidence. So basically, you invent your new theory and you invent it in a vacuum so that you don't have to basically explain anything that is already existing. So your theory is created in a vacuum that's got no evidence around, that justifies the existence of your theory. Okay, then she also makes the point, you adjust your theory so that you can have a theory make a prediction. Your theory can make a prediction. Okay. And then the last point that she makes is your theory will never be validated by any experiment. So you've got this theory and it can't be validated by the experiment. Okay, now what her point is, kind of this is getting to the science philosophy point. She's answering why the theory can't be validated by experiment. She says the number of theories that can be created by scientists using this inventing of an unnecessary theory, avoiding any conflict with evidence, adjusting the theory to make a prediction. You're never going, you can make an infinite number of theories, okay? And because there's an infinite number of theories, the chance that your theory will ever be validated by an experiment is equal to 0. Okay. And here's the punchline. The benefit of doing this is that there are an infinite number of papers for scientists to write and publish. So they can just keep inventing theories ad infinitum over and over and over, as many as they want, because that allows them to publish as many papers as they want. And because there'll never be any experimental validation of any of these theories that they're being made up, they can continue to publish and keep publishing and publishing. So, and the objective is to publish as many papers and get as many citations as possible so that you'll look good to the review committees when you come up for tenure. That's what I believe to be her thesis. Then we have here kind of some of my comments. There's a lot of puzzling new terminology in there. There's something called dark radiation. And it turns out that dark radiation is really the dark matter equivalent of regular radiation that we're familiar with, light. So you might think of dark radiation as being dark matter photons, okay, or dark photons, because they're the photons that dark matter interacts, how dark matter interacts with dark photons. So dark matter has physical properties and it does things. We don't know what it is, but they interact with photons that are dark photons or dark radiation. Then there's this thing called darkzilla dark matter. Why are they calling something darkzilla matter? Darkzilla matter. I have no idea. Okay, then this is one of the few ones I was able to figure out what they're talking about. Reheating. Reheating, I talked about this earlier. That supposedly occurs after inflation stops. And this is apparently true for even the standard Big Bang and the dark Big Bang. So reheating, I didn't know what that meant. That's why I bring this up. Then they start talking about dark scalar tunnels in their paper. I have no idea what dark scalar tunnel is. Next, they have dark sector scalar field called phi. This is really basically the creation field. So when this inflation happens, apparently this energy field of and they consider it to be a scalar energy field, exist, and this is the field from which dark matter is created. So the dark matter comes out of this dark sector scalar field phi, just as vacuum energy, or whatever the terminology is that they use, when the T equals 0 happens, there's a bunch of energy in the universe, okay, and that decays into matter. So the energy in the beginning becomes matter. And so this scalar field phi is what decays into dark matter. Okay, then they have another phrase here called dark plasma. Not sure what that means. That's kind of like. Then they have vacuum bubbles during phase transition. Phase transition, I think, is when the energy field decays to create matter. I think that's what they mean by phase transition, but I'm not really sure. And that's when the particles occur. So the particles apparently occur when the energy field decays, and as the universe is expanding, the energy field decays. And apparently this is when particles come into existence. And so you can have a field for the standard creation of standard matter, which they call visible matter. And you can have a parallel field called the phi field, which creates darkness. Okay. All right. Here are some of my comments on final puzzles. Dark Big Bang phase transition generates strong gravity waves. Okay, so this is the whole basic bottom line of the whole thing, which is they've created this scenario of creating these bubbles and boundary walls of the bubbles, and it's like a pot of boiling water, and all these bubbles are bubbling around and they're crashing into each other, and this is all supposed to create gravity waves. And those gravity waves have a spectrum, and they claim to have calculated the frequency spectrum of these gravity waves, and that this can be detected in some gravity wave detectors, which they don't go into. Apparently, there's a whole bunch of experiments of new gravity wave detectors that supposedly can be used to detect all this. Anyway, okay, so my final comment is this looks like an attempt to claim dark matter exists by hypothesizing a new way to detect it, despite the failure to detect it by conventional means. So this is a whole scheme to claim that dark matter exists because these gravitational experiments are going to apparently detect the spectrum of dark matter creation in the universe. And when they do that, then they'll be able to say, yes, we've proved that dark matter exists. And that's really the whole goal of this whole scheme. And that's kind of the end of my little presentation. And we have dead silence. No questions, anyone?
By the way, let's see, is mine on? Can you hear me?
Yes.
Here,
Can't see you though. Oh, we see a picture of you. We can hear you.
A deep scientific insight here is that Darkzilla, I think, is a play on words with Godzilla.
Yeah, but I have no idea what they mean by that.
Well, I think Hossenfelder is, being funny here. It's
No. It's in their paper.
oh God.
It's in the abstract, I think. It's in the abstract.
Okay.
And who knows where you can make a lot of comments about this. And one of them is you really have to be familiar with all the jargon. This is just full of jargon. But I found it interesting. There were two things I found that were interesting about reading this paper and looking at this. And one was I didn't really understand how the early part of the Big Bang was supposed to work. And so it kind of helped me to understand a little bit more about what they were talking about by puzzling through some of the jargon. And I didn't really quite understand exactly how the scenario was supposed to work. So for me, it sort of clarified a little bit about that there's an energy field at the beginning, and then this energy field, there's an inflation, and then this energy field decays to create particles. And it wasn't really clear to me how this scenario works. So I kind of gained a little bit of understanding about what they're talking about and a little bit of understanding of their jargon, which I thought was helpful. So from that point of view, this may have been a useful exercise for me. I don't know if it was a useful exercise for you others or not.
Yeah, it's too bad the Hassenfelder uh, doesn't pay more attention to the CNPS because I think we're kind of totally in tune with what she's saying.
Well, I have to tell you, she's a 100% Einstein supporter. She thinks Einstein is 100% the greatest. You know, she's got this little Einstein bobble doll on that she always mentions Einstein. She in every video she mentions Einstein. I mean, it's like every video has to have a mention of Einstein in it. And so, from my point of view, my guess would be, she wouldn't find any criticism of Einstein, which exists in the CNPS, to be anywhere near. Do you understand what I'm saying?
Yes, I do. I didn't realize that.
That's my take on her. She's not a critic of Einstein, so you can look at it from the point of view of she's kind of missed where the real root of the problem starts. She's criticizing the way current physics is operating and doesn't really realize that a lot of her criticisms, if we go back to the slide with the criticism, and I would say that some of these things that she criticizes, her criticisms, I would say they're completely valid for Einstein's special relativity in general for Einstein, but she doesn't see it that way. I mean, invent an unnecessary theory. Why do we need special relativity? It's it's like it's a completely unnecessary, misleading theory that leads physics down the wrong path. She's criticizing current physicists for doing this, but she doesn't see that Einstein may be the originator of it.
Yeah.
Well, Sabine seems to fit the definition of a social engineer.
Not sure what you mean by that.
Well, a social engineer attempts to manipulate opinion in certain
I
directions.
see. Well, she's one of the things I've noticed a trend is she's really critical of, and there's other people who are critical of this. They're critical of the fact that they think physics has lost its way, and I think that's really the theme of her videos is that physics has lost its way, and she's kind of on board with this criticism of that viewpoint. She's a proponent of that viewpoint, as you said, a social engineer. She's essentially creating opinion around the idea that physics has lost its way. And
that's what social engineers can do. You want to deflect attention away from possible real solutions toward the sort of word salad discussions, which begin with nothing and end with nothing.
Well, yeah, but my point is, and I think I made my point pretty clear. I think it begins with Einstein, and until you go back and fix the foundations, which means you have to go back and you have to fix Einstein. They're not prepared to do that. So Sabine is critical of current theoretical physics, at least that's my understanding of it. Unziger, I do believe, is also a critic in the same vein. And there are also other channels on YouTube that you can find that are critical in a similar sort of vein. But none of them go back and say, maybe we should be looking at the foundations, such as Einstein, because he apparently appears to be sacrosanct.
I'm not quite clear on Sabine's antecedents, but it could be said of her what is sometimes put to us, that I think she may have started, in conventional academia or conventional physics, and maybe, career prospects didn't sort of materialize. And it's sometimes said that, that can push people into dissidence. Maybe we're accused of that at times. I think she might be a bit in that category, if I'm not mistaken. That
Well,
she
I
might.
don't think you're mistaken. I think you're correct. I've seen the videos where she's talked about that.
Right.
And so, yeah.
In one place, I saw that she had stated that she had lost her funding, that her grant proposals
Correct.
were accepted.
I'm not. I think though that there's more than just. If you could talk, I don't really like the idea of taking her as an isolated example. I don't think what she's saying is an isolated example. I think Unziger is talking about the same thing. I think there are others, although I can't really put names to them right now. But there's a lot of videos that you can go on there where they'll say that the Big Bang Theory is in trouble. Modern physics is in trouble. Modern physics hasn't made any real progress. Modern physics is in stagnation. And of course now it's not really. You could argue that a lot of this talk is just talk to get clicks and views, by creating controversy. But I do think there is some substance to it, and it's becoming more than just an isolated opinion.
You're absolutely right, Harry. Yes, you're absolutely right. But let me give you one comment only. The most important part, these papers published by the most respectful journal, Phys Rev D. It's the highest level of publications, of papers. I cannot understand it at all. It's a continue the same Big Bang bullshit, I don't know, it's a catastrophe. On one side, we have Sabina and Unziker and all of them criticizing what we have with Big Bang, and now we have a new Big Bang. We have a new top papers in our physics. Totally unacceptable, guys. I'm very impressed. It's very important to tell that the highest level scientists, they accepted this model, which one will be confirmed. Never. I am absolutely sure. There is no physical meaning for it at all. I have no words.
That's what Sabine is saying, basically. And she's saying
I agree with you. I agree with you. It's not only her. A lot of guys, they're criticizing the Big Bang model. And instead of criticizing and continue and propose something different, they're trying to produce right now second Big Bang, dark Big Bang. Can you believe? Instead of one problem, we didn't solve it. We multiplied this problem. We multiplied it. Instead of the first one, not so clear. Right now, we're totally unclear model of dark Big Bang. I don't understand. I'm very frustrated with situation in physics right now.
Okay, we're back. As I was saying, I think the issue here is that they've got this idea of dark matter, which has become essential to their whole business of thinking. And they haven't basically, there's no experimental confirmation that dark matter exists. So that's a problem. So I see this as a twofold attempt to, one, find some way that they can prove that dark matter exists, given the failures that have happened for the last 20 or 30 years, or how long it is, I don't recall. They've never found any evidence of dark matter. So this is another way to justify spending money in their pursuit of finding dark matter and proving that it exists. So I see this as justifying spending a lot more money to do experiments to find and prove the existence of dark matter. So I see this as a part of the funding scheme.
Harry, I just have one point to add to your chart about Sabine's criticisms. it was talking about why theories couldn't be validated or invalidated, and there was a bullet about because there's an infinite number of theories. But I think it's more that because these theories have a huge number of parameters, that a single theory cannot be validated or invalidated because they just change one of the many parameters. And the other technique is that if there's a bridge between theory and empirical data, they just invent something new to bridge that gap, like dark matter or dark energy or inflation, etc.
Yes, I basically was, to be fair to Sabine, I basically just was summarizing what she was saying based on what I thought, what my impression was.
Yeah.
So, and there's a lot of these techniques of avoiding falsification. Special relativity specializes in the technique of avoiding falsification and claiming that experiments prove special relativity is correct when they really don't. And in the case of GPS, claiming that GPS proves relativity is correct, when in the case of the special relativity part of it, it doesn't. And of course, they also did that with the Haefel-Keating experiment. And so interpreting experimental results to favor your theory is another avoidance technique. So, there's a lot of techniques that are used to prevent theory falsification. This, I believe, this Big Bang, what they're talking about is an attempt to avoid the falsification of dark matter because it has to exist because they can't explain what's happening without it. Their their Newtonian theory of gravitation and Einstein's theory of gravitation fails. And so they have this hypothesis that there's this additional dark matter that explains the failing of their theoretical interpretations. And so this is a way of avoiding falsification. I think that this is an avoided falsification technique.
Yeah, special relativity has the advantage that Einstein stole all of his equations from a correct theory. So if you use the equations naively and think you're using the special relativity physical model, you can come up with the correct numerical answer, but that's only if you're really using the Lorentzian model.
Well, my point in bringing up special relativity was to basically make the point that a lot of these criticisms that we can make of modern theories or modern cosmological models, we can look back and see the same sorts of problems in special relativity, which we're pretty familiar with because we've worked over that topic pretty thoroughly.
Right.
So, Harry, can you explain a little bit about why dark matter is so vital to mainstream science in explaining, say, galaxy formation? Because you mentioned that Newtonian law doesn't seem to work for, say, galaxy rotations, but this whole the whole model name is lambda cold dark matter, right? So how is that needed? Do you know?
Well, dark matter has to exist because of the fact that you just said it yourself, to explain galaxy rotation curves. I did a whole discussion about the presentation about dark matter and this. There's the problem with the velocity of galaxies and clusters. The velocities of the galaxies and the clusters exceed the mass that is supposedly existing in these clusters.
Yeah, but I see that there is some beside that. they're like, if you ask the mainstream scientists, there are like 3 or 4 reasons why dark matter should exist. And so the galaxy rotation thing is one thing. But then there's this entire, like I said, about the lambda cold dark matter model, which is,
Well,
I
now
don't know, like the main Big Bang model, right?
okay. So here's the point. The point is the lambda CDM model is an attempt to explain where the dark matter comes from. So you have to, in the Big Bang theory, or the modern version of it, the lambda CDM model, they have to have two things in there that didn't exist in the Big Bang model that was originally proposed. That is dark energy and dark matter. So those two things have to be somehow added into the cosmology. And dark matter was added in first for the reasons that we discussed, which was how does dark matter come to exist? Because they need dark matter to explain motions of galaxies and the rotation curves. And then the lambda part is the dark energy part, which came in around the 1990s. There was a discrepancy with the observations, which led them to conclude that the universe was expanding faster than it ought to. And so they needed a dark energy component to explain that. So the lambda CDM model is the lambda is dark energy and CDM means cold dark matter. And so that's the new Big Bang model. That's the old Big Bang model was modified, 1, to add inflation, 2, to add dark matter, and 3, to add dark energy.
So the lambda really is more about the dark energy, because that's what I was confused about. It's like, do they need dark matter to explain the big parts of the Big Bang? Or I thought maybe I heard that, like, if you look at galaxies, they're spread out in filaments and bubbles, and that dark matter was being invoked to explain those structures. Is that true?
I can't answer that. I really don't know the answer to that. Maybe somebody else can answer that.
See, I think in a way, at present, it's even more trivial than that. I mean, you're talking about the origin of these expositions, dark energy and dark matter. That's right. But now they've come into common parlance. They're now on all the journalists' lists. And, the common people are using dark matter and dark energy. So the system, I think, of, modifying any existing experimental evidence or anything like that to accommodate these conceptions, which are now imprinted upon the mind. So it's become post-scientific, actually. You have postulation of these things to try to explain something, and now they've become dogma. They've become something which is unquestionable.
Yes, I'm not going to argue with that.
Let me mention about Franklin's first example about dark matter being needed to explain the rotation rates of stars on the outer part of the spiral galaxy. That was done because they made a mathematical error. It is not needed. Newtonian physics explains that perfectly, the data perfectly. What they did was use the Newtonian gravitation as though there was spherical symmetry, and there is not spherical symmetry in a spiral galaxy. If you use the equations correctly, as a number of people have pointed out, Newtonian gravity explains it perfectly. So
yeah, the question is, how can 10,000 astrophysicists be wrong? That was my main question, because it's so obviously wrong. Any fifth grader could tell you that, but how is it they spent $1 billion searching for dark matter and not realize that?
I think that's something that Jim Keen probably has a better answer for. social engineering, I guess, as Jim King would sort of say.
Actually,
Everyone be
my
so
answer
blinded.
was in the presentation I was scheduled to give.
Yeah, in fact, we're in the second meeting, so perhaps it is a segue to your presentation.
Well, I guess I could do it in the third meeting. Or
Why
just
don't we just segue
it seems
into
like everybody is interested in talking about the Big Bang,
well,
which is fine with me. I mean, people should talk about what they're interested in.
well, let's hear what you have to say, and then in the third meeting, we can basically, hopefully, I'm not sure how much time is left, but probably only about 15 or 20 minutes.
Yeah, because nobody told that it will be enough the third session. Gene, start now, because then we will have some discussion of your model.
We've got about 30 minutes in the current session, I think.
Well, my screen says there's 12 minutes and 40 seconds left.
All right, go ahead.
No, probably more accurate.
Oh, okay. I'll need to share my screen. I sent the request to share my screen.
It's approved.
Okay. Let's see. I need to get this great. Some curious features of Newton's. This is an introductory slide. Newton defines gravitational force F as the large capital G times two masses, mass 1 and mass 2 divided by r squared, while Einstein's general relativity asserts that gravity is not a force. Although general relativity curved space-time reduces to universal gravitation, flat geometry, when space-time curvature decreases to 0. A second curious feature, various operational definitions of mass, M1 and M2 above, may give somewhat different values comparing weight measured on a scale, 2, atomic number of an element, 3, neutron mass not exactly equal to the sum of proton and electron mass, and 4th, the universal gravitation inferred mass. This is a term I'm introducing here today. The Cavendish experiment aimed to weigh the Earth. Earth mass could then be inferred using Earth's radius and density. Next, we had double our twice removed inferred mass of other planets, the sun, and beyond to galaxies based upon Earth's inferred mass and Newton's universal gravitation. On another front, another curious feature is compared to other measures like light speed c, elementary charge E, and Planck's constant H, capital G measurements have exhibited more variation in obtained values and confidence intervals. In the Wikipedia article on universal gravitation, there's sort of a nice figure which summarizes this history, showing the variation in attained values and confidence intervals by various investigators over time. Now, Newton's gravity law, is that an honest mistake or intentional hoax? Let gravity denote standard gravity, small g, the observation of acceleration of objects in meters per second squared toward other objects, such as the Earth. Point 2, note mass in kilograms is not explicitly present in the observation of gravity g, quantified, as I just said, as length versus time squared. 3, Galileo and others before him, and there were many from what I've been rereading, noted that this observed acceleration g was independent of object mass. We have the, so-called Leaning Tower of Pisa experiment, and others had apparently done this same sort of experiment previously, even to Galileo. Thus, at least 50 years before Newton's work, the lack of a relation between mass and gravity G was demonstrated and known by many. 5, possibly Newton was unaware of this no result between mass and gravity G. If so, this favors the honest mistake option. 6, Newton focused on force as mass times acceleration. That's his second law, as we know. So he was inclined to relate the observed acceleration, gravity G, to his idea of force by adding mass to the story. This favors the honest mistake option. Point 7, this honest mistake led to the law that we know of, stated here, of the force equals the gravitational constant times the product of two masses divided by the distance between them squared. 8, widespread acceptance of this mistaken law set the stage for Einstein and many others to be completely tricked or hoodwinked into producing general relativity theory, also contrary to known fact that the observed acceleration, gravity G, was independent of object mass. 9, an alternative is that Newton knew about the independence of gravity G and mass, which favors the intentional hoax option. 10, if Newton knew previous results showing mass gravity independence, then he would probably have been aware of the logical inconsistency of asserting one object's mass, say m1 above, has zero relation to force F, while the other object's mass, say m2 above, is related to the force. If so, this favors the intentional hoax option. 11, remaining question, the motive for Newton's hoax. Perhaps to show how gullible the intellectuals of his time actually were, possibly revenge. Back in those days, the same things were going on as we see today. For example, Newton was in a big dispute with Robert Hooke, H-O-O-K-E, with regard to some of his work with light. So there could be a revenge motive involved here. That's very speculative, of course. Some consequences of the failure of Newton's universal gravitation law. Universal gravitation failure has had major adverse effects in cosmology. When universal gravitation failed to account for astronomical measurements, instead of recognition that universal gravity was wrong, astrophysicists postulated that the missing mass, according to universal gravity, was actually there, but we just can't see it or detect it, namely the theory of magic dark matter. Another point, universal gravity constant G may be compared to a carnival trick to deceive where the gullible public always loses their money. The con artist says that gravity G equals a big capital G times the mass divided by r squared. This deception may look reasonable since small g is inversely proportional to distance r squared. But behind the curtain of the carnival trickster, G does nothing more than remove mass from the equation and set correct dimensions. Many particle physicists accept universal gravity. On another front here, universal gravity failure weakens the scientific merit of defining each force by a type of particle interaction. Further consequences of the failure of Newton's universal gravitation law. So the GM term in small g equals big G, m divided by r squared, acts to remove mass from the game to conform to the known independence of mass and freefall gravity g. This mass removal is done with the kilograms raised to the -1, in other words, 1 over kilograms term in g. That's where the sleight of hand takes place to fool everybody. Thus, the g times mass term needs to be replaced excuse me, with some other value x, where g equals x divided by r squared is consistent with observations. X may be determined partly by the law of motion in binary mechanics. Why has universal gravity failure not been widely recognized? Well, for one thing, ad hoc hypotheses like dark matter can effectively hide universal gravitation failure. One factor may be that object mass is correlated with gravity g mechanisms described by binary mechanics. For example, planet radius relates both to the planet's mass featured in universal gravitation, and secondly, the law of motion or motion mechanism proposed by binary mechanics and documented by the Casimir effect, lunar laser ranging data, and GRACE satellite data. And that concludes my presentation. Wow, and we're 23 seconds left. That was timed perfectly. So you are here today, the witnesses of the death of the universal gravitation law. This is something you'll tell your grandchildren, that you were there when this happened and you witnessed it firsthand. So be sure to put that in your diary.
Okay. I'm not sure I can say that I understood it. I think I probably need to know more about binary mechanics.
Well, binary mechanics comes into the picture only in terms of what the value of x is in the new version of Newton's law. You don't need to understand anything about binary mechanics to understand why Newton's law, gravitation's law, is a falsehood, is wrong.
You see, I would say that contraries, if you permit me, that Newton's universal law does actually give the correct results. Now, for example, if you ascend the Leaning Tower of Pisa and drop two masses, you drop a very heavy one and a light one to the ground, and you have a very accurate way of measuring how long it takes to descend and when they hit the ground. They will hit the ground simultaneously, that is true. However, if you then do another experiment and you go up to the top of the tower and you drop the heavy mass and you find how long it takes to descend, and then you go up separately and you drop the light mass and you compare that, you find how long it takes to descend. Well, you'll find that they're approximately the same, but actually if you have a very, very accurate experiment, you'll find that the heavy object does drop very slightly faster. In other words, it takes very, very small amount of time less to hit the Earth. Now, the reason for that is that, very strictly speaking, there isn't just a force between the Earth, gm over r squared, between the Earth and the object, but there's also a converse force between the object and the Earth. Now, the difference between that force, the huge mass of the Earth and a very small mass, well, there is a theoretical difference between a very, very high, large mass on the Earth and a small mass. Now, when you drop the two masses simultaneously, you have M1 plus M2, let's say, heavy mass plus light mass, and they're falling simultaneously and they're attracting the Earth simultaneously. So there's no difference. Like it's the sum of the masses. But if you do this experiment separately, you will find difference. Now, Newton's law, shows this because what you, with respect, Jim, are calling either a sleight of hand or an ignorance or something, this sort of cancellation, of the m, say large M G equals G large M over the large M cancels. Well, if you actually look at it in terms of frames of reference, you will actually see that you have to have large M plus small m multiplied by G, over R squared, because, you have a very, very large force between the Earth and the object moving in one direction, and then you have a smaller force between the object, which is attracting the Earth. And if you look at this in terms of absolute space, you'll have m1 plus m2. So basically, that's a long, long way of saying that if you look at all these different ways of looking at the thing and very, very detailed experiments, you will find, so I maintain, that Newton's law works. It works perfectly. So therefore, I would fail to see how you say it's almost bogus, Jim.
Well, for one thing, you indicated that there's a very, very slight difference that between the heavy and light objects when they're dropped at different times and so forth. Well, Newton's law means that there should be a huge difference. So the last point, the last paragraph on the current slide at the bottom there does indicate that there is some correlation. Now, correlation doesn't mean causation. That there is some correlation between the involving planet radius relating both to its mass and the law of motion in binary mechanics. So again, I think we've sort of witnessed the death of Newton's universal gravitation law. All the evidence seems to point to that there could be some very minute, small percentage, as Ian just pointed out, of apparent validity to the law is itself evidence against the law. That it should be 100%. But everyone knows it's not 100%, that the two things are independent.
Okay, we got 10 minutes. Just a kind of a question, a historical question on this, on the side. What has brought this up to your, why are you thinking about this? What has stimulated this thought process in your mind?
Well, I to some extent, I have to thank Harry.
You're thanking me.
Discussions, because it's obvious that the whole genesis of this idea of dark matter, is simply a way to not recognize that Newton's universal gravitation law is wrong. So that we've been focusing on Einstein and special relativity and so forth as being wrong. Well, I think we ought to go for the throat. And the throat here is Newton's universal gravitation law is wrong. Okay, we already know that some of his other concepts are wrong, are inconsistent with evidence. For example, angular momentum is not conserved independently of linear momentum being conserved, that the two items are interchangeable as shown by inertial propulsion phenomena and gyroscopic devices that levitate satellites and so forth. So we already know that Newton's three laws are subject to a lot of questioning. Not to detract from Newton, he did a great job in advancing science and mathematical science and so forth. but there are flaws, and certainly his gravitation law, I mean, needs to be completely dumped, and we need to find the other value. In my second point on the slide shown now of X, to replace the product of big G and M, because big G and M just takes mass out of the relationship. As I show in the first point, this mass, to repeat, this mass removal is done by the 1/kilograms term in the G constant. So even Newton himself says that mass is not important, you know. So I mean, it's all a carnival flim flam, and until we recognize these basic flaws in what we think are, sacred, unquestionable things, we're not going to find out what the X value is. What we should be focusing on is in the second point in the slide there. What is X? Binary mechanics has some answers, but that's, not, that's a point that's not even relevant to the argument I present today that Newton's law has failed.
Well, let me ask you a question to interpret, and that is, how are you interpreting the physical meaning of Newton's law? Are you doing it on a total mass basis for the object, or on a unit mass, like for when we talk about what is it? Potential energy. That's potential energy per unit. Okay, so I don't think Newton's law is supposed to be interpreted as that a steel ball that's twice the mass of another steel ball will fall twice as fast. It's saying that I think the gravitational law works well in terms of orbits and whatnot when you have two very large masses.
You really can't state what it is saying.
Well, I think if you think of it
perhaps
as a force,
say, hey, we don't know what it's saying.
Yeah, but it's the force.
What it's saying does not make any sense in terms of actual observations.
I have a few questions I wrote in the chat. Well, okay. Well, do you mean to suggest that objects don't accelerate towards each other through gravity?
Well, gravity is a label. It's a word.
What's up?
A word which is denotes,
among other things, trying to get ready for you to come by.
Acceleration of objects. Well, let's let Robert Kemp speak. Go ahead, Robert. Robert, go ahead, man.
Are you muted? He's muted.
Well, I have other questions as well.
I'm not sure. I think he was talking to somebody else.
Well, he shut off his audio, so I thought I would jump in.
Go ahead, Jerry.
Okay.
All right. Before we get on here, I just want to point out there's like 4 minutes left, so we can't get too winded here.
Oh yeah. Okay. I'll be brief. If Newton's equations regarding gravity weren't correct, wouldn't there exist an alternate equation that would explain this? Even if gravity is a result of curvature of space-time, which I'm sure you don't believe, but wouldn't there be an equation that would explain this and how to arrive at that?
That's my second point in the slide being displayed now. There is your second equation, X. We need to find out what X is. Binary mechanics has some ideas as to what X is, but maybe that's wrong. So that the field is open to investigators to tell us what X is in the correct equation, which is given in the second point on the displayed slide.
I agree with that, and I'll tell you what X is. X is G M1 plus M2. It's the sum of the masses. So that's why the mass
there's no book that says that, Ian.
Say again, Jim?
There's no book that says that.
If there is, because
The equations
there's
that I've
confusion.
seen are G equals small g equals big G times a mass divided by r squared.
Yeah, but the textbooks, so I would maintain, Jim, are confused here. They don't make it clear. What they're doing is they're taking the Earth to be an absolute frame. Again, it's relativity back again, and they're looking at it from the point of view of the observer on Earth. But if you actually look at it from the absolute frame, what I defend, outside the Earth, so the Earth is actually moving towards the mass very, very slightly, and the mass is moving towards the Earth very greatly. Well, if you do it in that frame, the masses don't actually cancel out. You have small mg on one side, and you have g into large M plus small m over r squared. So I suppose in a way it's a bit hard to talk about this so quickly, but in a way I'm saying I do agree with your concept, but I would claim that correct interpretation of Newton in the correct frame of reference actually does lead to what you're saying, Jim.
Jim, what are the well accounted for observations of that objects when they attract through gravity that they accelerate towards each other? Would you say you disagree with all of Newton's laws of motion?
No, I've already questioned the conservation of angular momentum and conservation of linear momentum, since those are somewhat interchangeable, but that's a whole nother day. For today, the small g is based upon the observation of an acceleration, and it's measured in meters per second squared. It's an observation. Okay,
that's not true.
We put the label gravity on that observation, and we call it small g.
Are you conflating the force, actual weight force, with acceleration? Because the gravity force is, say, measured in pounds. That's when you stick a bowling ball.
Hold on. We're coming up to the end here, so why don't we hold our questions for the next session?
Franklin, it's not measured in pounds. It's measured in newtons.
Which is a measure of force, which is the same thing.
Pounds is a measure of force?
You can convert it directly into newtons.
I thought pounds was a measure of weight.
Poundal would be the
weight only applies
equivalent.
Gravitational force acting upon mass. Gravitation, what weight? Mass has weight when there's a gravitational force. It's specifically on Earth or gravitational, large gravitational fields such as planets, the sun. I would say.
Well,
yeah.
Again, I think I was making the same point as Ian when I'm talking about how you physically interpret the equation. I think you're interpreting it in terms of two total masses, where it's really on a unit mass. The mass of the Earth, it causes acceleration on a per unit base, and vice versa.
Well,
so from that's
the story. That's not what all the textbooks, the equation, the first point in the display slide, actually mass is removed by the constant big G. And how it is done is there. And so, I don't know why anyone has a problem with that. Mass is removed from the acceleration. So then that opens up the question of what is causing the acceleration if it's not mass. Exactly.
Potential energy is measured on your potential energy at a particular point above the Earth is measured on a per unit basis.
I don't know what that means. I guess you're trying to take a shot at what the value of X is in the second point on the slide?
No, I'm just talking about
and you're trying
explaining
to
the
say, well,
physical interpretation of Newton's universal gravitation law. It produces a potential, and it's the same potential out of, at a particular altitude for all
but you've
substances
got a
per
problem.
unit mass.
You've got
You
a
expect
problem there. If the acceleration of free fall gravity, small g, is independent of mass, you're saying that a potential is created by something which is not in the expression.
Do you know
No,
why that
no,
is?
it's dependent on the mass of the Earth. And
I
if you
mean, do
want to
you guys
know,
understand why it is that the acceleration of gravity is independent of the mass? Do you guys understand? It's a very basic physics concept that the reason why a 10-pound ball falls at exactly the same rate as a 1-pound ball is due to inertial resistance. Inertial resistance is a force that resists any force. Like if you are pushing a loaf of bread versus a Volkswagen Beetle, the amount of force in newtons is much greater to press the very large 1-ton vehicle, because the amount of inertial resistance is actually proportional to the amount of mass. So a 10-pound bowling ball is going to present 10 times more resistance to acceleration than a 1-pound ball. So that the reason why the 10-pound ball is accelerated at exactly the same rate as the 1-pound ball is because the 10-pound ball takes 10 times as much force. So that's Newton's law is expressed in newtons, as you say. Newton's law is not expressed as an acceleration, right? The 9.8 meters is not any measure of the force of gravity. That is just the amount of newtons, which is what Newtonian law, that's its units, against the amount of inertial mass that's present. So it's like you get it in order to accelerate the 10-pound ball, you have to apply, say, 10 newtons to it. But you have the 1-pound ball, which only has 1 newton of gravitational force on it, but yet it can accelerate it at exactly the same rate as a 10-pound ball because it has 10 times less inertial resistance. So I was just wondering, do you understand that concept, James, of inertial resistance? And that's why they say 10-pound ball accelerates at exactly the same rate. It's just the inertial resistance is exactly proportional to the mass. So
I guess that's an effort to save Newton's universal gravitation law.
Yes, it does. I think that does totally save the Newton's gravitational law, because that explains why, according to Newton's gravitational law, why all objects should fall at exactly the same rate. Because you would have to accept this concept of inertial resistance, because there's other weird things like if you.
So you're saying there's
Einstein,
really another inertial resistance law?
Yes, and that definitely
gravitation
works. There's definitely an inertial resistance law. You can test it, you can do experiments, and you can find out that inertial resistance is exactly proportional to mass, which is another mystery. Why is it that? Because these two forces exactly cancel each other out when it comes to acceleration. Now, maybe that could be maybe the real problem here, because there are other theories. They say
the
why.
Earth. This is true on the Earth, but see, on the Earth, we take ourselves as the absolute frame. So the fact that we in the Earth are being attracted ever so slightly to this mass is not taken into account, because we are stationary by definition. But if you were in an absolute frame, a theoretical absolute frame, in absolute space, you actually would find what Jim is saying, that the masses don't cancel out. But I claim, I think Robert has the same idea here. It's just the sum of the masses times g in the absolute frame.
I mean,
which doesn't
it's just
cancel out.
the
So in other words,
gravitational
M on
law
one side
with,
of the equation and
with
M
the
plus large M on the other side.
So now you've got a new law of gravitation. Instead of the product of the masses, you have the sum.
Well,
So in other words, you're
well, the
really
problem is that
no,
Newton's
do you know what I say, Jim?
gravitation
I
law has
claim.
failed, and you're proposing another different
No,
law.
I say this.
there's
I tell
force
you what I
equals
say.
mass times
I say the
acceleration.
textbooks are wrong. Newton's laws are correct. The textbooks are not explaining it properly in terms
Right.
of reference frames of reference, and so therefore, your point in saying that Newton's ideas are wrong, I would say that the usual textbooks explanation of Newton's ideas are incomplete. I would say.
No, I think there's F equals ma. You guys heard of that one, right? Force equals mass times acceleration.
Right.
And so you use that together with Newton's universal law of gravitation to calculate. You have to calculate the expected acceleration. And if you use both of those, you find out that the what we observe, which is a 10-pound ball, should accelerate exactly the same rate as the 1-pound ball.
Right.
That's what you find.
And that's stating that the acceleration is independent of mass. That's exactly what
No, force equals mass times acceleration.
Franklin, you've stated it very nicely. Thank you.
No, the force.
My thesis.
Well, no, it doesn't. You calculate acceleration according to F equals ma. You calculate Newtonian gravity according to standard practices, and you calculate that you will always come up with 9.8 meters per second acceleration at the Earth. That's
on the Earth as well.
Well, that's not what you said just a moment ago. Thank God we're recording this, because it seems like we change our statements when we find that one statement doesn't work. Then we just go to another one.
No, I've said exactly the same thing. Force equals mass times acceleration. Gravity is g times m1 times m2 divided by r squared. Go ahead.
Well,
you just need to calculate what the expected acceleration is.
I have to admit, I don't understand the math per se that well, though. Why wouldn't objects accelerate toward each other through gravity? It's been thoroughly documented and observed. Also, why wouldn't objects at rest tend to stay at rest and objects in motion stay in motion in a straight line unless interfered with by another force? I mean, those are like two of his laws of motion. How are they incorrect? Even if binary mechanics is correct, I mean, why wouldn't this apply? It's thoroughly documented. It's observed.
Yeah, that's the value X in my second point on the displayed slide. We need to have an alternative to the GM term, because the GM term simply throws out mass. In terms
I
of
don't think that's
acceleration.
Well, that doesn't make any sense that it throws out mass. I mean, maybe dimensionally.
Simple algebra, Franklin. You can't argue with simple algebra.
No, the masses as they increase the force. So how can you say that it throws out the mass? I mean, maybe
I can say that by simple algebra. Look at the term G times M at the top of the slide.
Yeah.
The mass removal is done by the inverse kilogram term in G.
No, it isn't. If I say G.
Oh, so you're denying algebra now. Algebra is out the window. So you've got a new mathematics you are proposing.
No, it's simple. Just if you take that G equals G times M divided by R squared. So to make things simple, let's just make G equal to 1. So I make mass equal to 10. So G would equal to, G times 10 over R squared. Now, if I change mass and I change it to 2, then we have something which is 5 times less. G becomes 5 times less.
You're talking about values. You're not
still being used.
Dimensional terms.
Jim.
I'm doing a dimensional analysis. You're talking about specific values.
Yes, I'm talking about specific values. So the dimensional analysis I don't think matters. I mean, what matters is the actual force that comes out of it, because
Well, that's
the
a
force,
novel approach to physics.
Jim.
I don't know any serious physicist that discards dimensional analysis.
Jim,
the thing is that the dimensional analysis gets it to the different thing that you're looking at, which is force.
I'm looking at acceleration, which is an observed fact.
But G is not an acceleration. The G that's coming out of there is Newton.
The small g?
Small g that you have there, that is expressed in newtons. That is an expression of force, not an expression of acceleration.
Go back to your physics 101 textbooks.
Yes, I'm doing physics 101.
The
This
units
is
of small g are length divided by distance squared. In other words, the units of small g are acceleration.
Well, first of all, this formula you have here isn't
get out your physics
universal gravity law, so maybe that's the source of the problem. Because
the source of the problem is you need to read a college physics book, I think.
No, I'm reading a college physics book. The college physics book says force, the universal gravitational law is force is equal to big G times mass 1 times mass 2 over r squared. So I don't know where you're even getting this small g from. Where is this small g coming from? This is not any part of any physics
acceleration observed.
No, that is not the acceleration observed.
Well, look it up on the internet. What is it?
Look it up on the internet, you'll find that there is no little g term, because, like I said, the universal gravity law, its output is force in newtons, not acceleration. The formula that you have there, G equals G times m over r squared, you'll never find that in any textbook. You can look it up right now on the internet. No one will express Newton's universal gravity law as outputting an acceleration. That doesn't exist.
I think an interesting observation might be that this discussion is illustrating one thing, I would say. Like we all of us, I think, have experienced maybe going to the mainstream academia, and when we criticize Einstein's theory, they get quite emotional because they're very well wedded to the theory, and they marshal all these arguments. Now, it's actually illustrated to me anyway that we dissidents here, including myself, are very much wedded to Newton's universal gravitational law. And when somebody like Jim comes in and casts some doubt upon it, we're all up in arms, maybe trying to defend it, including myself. I claim that. So whatever the arguments for and against, it has introduced one psychological aspect, which I think is of interest.
Well, you see,
we're just trying to find out, what are the differing opinions, and if there is a different opinion, what is the source of the difficulty? So it's a perfectly fair argument to say that this formula G equals G times m over r squared. If G is expressing an acceleration, then no, that is not supported in any physics textbook.
G that doesn't support, G is not an acceleration. It's a constant, which has a certain units, and those units remove mass from the equation.
That's right, because it's talking about unit mass, per unit mass.
Well, once again, what is G then?
G is an observed fact. G is let's distinguish between theory and fact. G, as I said in my first slides up there, that is an observation that there exists an acceleration. Like when, for example, a certain satellite approaches Neptune or Saturn, apparently the instrumentation on this satellite, so I have read, can detect a slight acceleration toward the planet. And therefore we get the G value using the distance of the satellite from the planet's surface or center. That's your r squared in the equation. And but it's an observed fact that this acceleration occurs, so that as far as I know, it's undisputed in science today that there is such an acceleration. And what is also, I think, undisputable is that the typical equations presented remove mass from the equation by the units of the large g constant. That's what happens. That's called dimensional analysis. So poof, mass is taken out, and yet everyone says mass is so important.
The units are correct, and that dimensional analysis is correct. However, the correct expression should be small m, small g is equal to large G into large M plus small m over r squared. That's the absolute acceleration, relative acceleration between the Earth and the satellite, or the Earth and the stone. Now, large M plus small m over small m is approximately equal to large M. So, you know, it's for all intents and purposes, it's neglected. But actually, it doesn't cancel out. Dimensionally, yes, it's one mass over another mass. But it actually doesn't cancel out, because the effective mass is large M plus small m over small m.
Well, I acknowledge in the bottom point in the displayed slide that object mass does seem to be correlated, as Ian just and others are pointing out, with the gravity G mechanisms. Okay, so because planet radius does relate to both its mass featured in universal gravitation, and also the law of motion, or some other explanation for X in the second point in the slide. So that, yes, so that can be a point of confusion, but correlation does not demonstrate causation.
Well, now we have silence.
Well, no one can refute
No.
gravitation law has failed.
No.
No.
You look in terms of total mass instead of force per unit mass. If I have a 10-pound ball and a 1 pound ball,
history of physics. Can I continue? Please, James, don't interrupt me. Let me tell you the story. First of all, shortly after Newton, there was such a big guy, Lesage. He told already, even at that time, there is no force between M1 and M2. There is totally different story. He told that there are some particles with speed close to speed of light that penetrating two masses at the same time. And there is a screening effect. They have some weak interaction with each mass, and the flow of these particles between them is less than outside. What does it mean? There is some less pressure between them. First of all, Lesage told it's proportional to M1 and M2. That his explanation was.
You're talking about the Lesage theory. That's the French guy that has the particle theory of gravity, right?
Yes, of course. Let me continue, because you know it's only the beginning of the story. The second story, Einstein, in 1893, he transferred this gravitational, Newton gravitation, and all this stuff to gravitomagnetism. Gravitomagnetism, they have an equations approximately the same as Maxwell equation, except some constants like G, big one, and so on and so on. But what is important? It's a very important issue. If you are going to the field equations, you don't have the notion of force at all. There are only energy density and energy density flux. That's it. Simple like this. That's why the main point is not M1, M2 to something to reject and all this. No, it's our wrong definition for this effect. Force. There are no force. There is only less pressure between two masses. That's why this effect, of course, proportional to both masses. And then the issue is they will always interact together. Together means there is only acceptance to each other. There is no going out from it. You see what I mean? We must go to the field equations. We must go to gravitomagnetism. Even rotational curves, the guy he already proved that we don't need these rotational curves with dark matter. We don't need. We need only to take into account mass currents like it is in Maxwell equation. That's why, guys, we're talking about the non-existent notion, force. There are no forces in electromagnetic and gravitomagnetic. There are only pressures, there is energy density, energy flux density, that's it. And Lesage mechanism, it's exactly what explains what we have in our real life. First of all, the second one, G small, it's only valid for Earth. On a Mars will be different, only some other planets will be different. Why we're talking about G small? It's only convenience for us to calculate our so-named forces, but there are no forces. There is only less pressure between two masses because of my weak interaction of these penetrating particles from all the side, but screening effect between them. Simple like this. That's why you invented new law, some X parameter, and all this stuff. But please, first of all, take a look on the history of these equations, of all the transition from this gravitational law to the real gravitomagnetic field. And then you will see there is no really contradictions between all our notions. And for us, it's much more easy to use Newton laws and to put force and so on and so on. But there are no forces. There are no forces. Gravitomagnetism shows that gravitation, it's only some kind of parameter of the medium around, or some parameter of these penetrating particles through the land. That's it. It's only this one, guys. That's why I'm talking about something. We don't know why we're talking about it. I'm very sorry. Please, we must look for history of these ideas. And Heaviside already put in 1893, it's only 130 years old ideas. You can go to your Wikipedia, you like it, James, and take a look at gravitomagnetism, how he showed this gravitational law of Newton will go inside of this gravitomagnetism. Don't invent that rotation curves. It's a mass currents in this gravitomagnetism. It's exactly what I'm talking about all the time. Lesage gravity theory. But it's a screening effect. That's it. That's why we have all the interaction together. You know, they are moving to each other. There is no something outside, you know. That's why, guys, the beginning of your story, force, wrong, absolutely wrong. Don't even name it. It's for our convenience only. That's it. And measurements of force, accelerations, and all this stuff, it's our convenience. It's not explanation of gravity as a mechanism. Lesage, it's only 300 years old, you know, idea. Please go to history and you will find the right explanation what we're talking about today.
Okay. Yes. My comment on this is you're talking about gravito-electromagnetism, which is that big word. I can't even say it very well. And you're talking about Lesage's idea. And I don't think that I'm not really that familiar with it. And so that's kind of probably you need to
We must go to the history of this, gravity, and we will see this. It's exactly why I put in my model Lesage, because there is energy density going down, gravitational parameter is going down. It's simple like this. My
Okay.
model is only based on Lesage as a medium. We have energy density of the medium, we have this parameter as a parameter of the medium, cosmic medium in our world.
Okay.
Simple like this, guys.
So I really do like the principle of the energy density principle that you're using. To me, that makes more sense. So anyway, I understand that part. I'm not really sure that other people do. So anyway, my point being, what I was really trying to get at is, I don't really understand this electromagnetism stuff. I looked at it, and it's very unfamiliar to me. So probably we need to talk about this a little bit more to understand what the concept is. But I think what's interesting here is that we kind of do have differences of opinion based on dark matter is not really necessary. So we're talking about where the problem is. Why we're, we got this dark matter thing that mainstream is sort of invented to fix a problem, and we're trying to figure out where the problem is, because we don't really think dark matter really needs to be in our concepts of how the universe is organized. We don't really think dark matter really is a concept that needs to be in our theories.
But we cannot do this conclusion based on the wrong iteration. We are talking about the gravity, Newton, and so on and so on. And based on our wrong interpretation of this gravity as a phenomenon, as a fact, and all this stuff, we are trying to cancel there is no dark matter. What is the reason for it? We don't have it. Even this, the report presentation, what we have right now, it's wrong, because the very first notion, false, wrong. Simple like this. It's only our convenience, and that's it. Simple like this. And it's not electromagnetism, it's a Maxwell equation. Gravitomagnetism, it's analog of Maxwell equations. And what is important is 130 years old idea. Heaviside, he was a great physicist. I'm so happy to find out all these genius people, they go long time ago, 200, 300 years, 100 years ago. We have no idea about the physics and history of our physics. That's why we speculate about some ideas from school, and we don't know where it came from. That's it. Simple like this. Guys, please pay attention to history. Take a look on a Heaviside on Wikipedia, and you will see all these equations, what he proposed, and why it's going on, and so on and so on. And Lesage too, because Lesage from the beginning told there are no forces. There is only screening effect. That's it. And that's why we have only, the moon going to Earth, not outside of the Earth, because of the screening effect.
Okay, we're under 10 minutes now.
Okay, we have two issues. One was, is there something fundamentally wrong with Newton's gravitational law? And I think a number of people have made points for James's consideration. I'll just add, try and say my one point in different form. He says that you've eliminated mass. No, you haven't eliminated mass. You put the equation in the form of per unit mass, which is done in a number of areas of physics. And there's no problem with Newton's gravitational law. It may be that a better law is being articulated by Vladimir or by somebody else. But that's a qualitatively different issue.
I'm sorry. Even the notion mass depends on this Lesage mechanism. I will tell you why. Because it's emergent phenomenon. Mass, what does it mean, mass? What your notion of mass? James, what does it mean, mass? kilogram, pound, it does matter. What does matter? What is this notion about? And according to research, it's, the interruption of your flow of some particles, and you have your mass because of weak interaction of these particles with these objects. You see, even mass, it's emergent phenomenon. There is no mass between particles. It's a bullshit. There are only macro objects. You must interrupt your flow of these particles from both sides. And only then you can introduce even this notion mass. Guys, it's macro object mass. It's only gravitational mass you can introduce only this way.
So
You have
Vlad
your
agrees
mass. What
that
does it mean, your mass?
that not only does he agree with the removal of mass from Newton's equation, but he also says that there is no mass. So
Yes, as it is, it's our convenience, and that's why don't blame Newton. He was a genius guy for that time, and so on and so on. He found some relations between masses and all this stuff, and don't try to correct it. First of all, go to research, then to go to heavy side, and you will see everything is okay with Newton. Sorry.
Yeah.
Okay, we're getting close to the end here. I'm going to sort of I see there's some issues. I want to throw out my idea. When you start talking about electromagnetism, analogy to electromagnetism, it seems to me that when you bring two masses together, there's an induction effect like you get with electricity and magnetism, where when one magnet approaches the other, there's an induction and they react on each other. So you can't exactly use the Newton law formula because the interaction, as they get closer, the force isn't exactly predicted. There's an induction effect that takes place. And my thought is that this is really why there's a mistake in the quote gravity law, because they're not taking this induction of gravity. There's anyway, do you understand what I'm saying, Vladimir?
Yes, but let me tell you, you're talking induction means force. There are no forces. This is my point. The most important, there are no forces. It's our convenience to introduce them.
The energy density, though, is changed by the interaction. That's the point.
But interaction means force.
Well,
it's exactly my point. We use some notion force. We use some notion mass, and we are speculating around some notions. We don't know what does it mean.
Okay,
it's exactly my point, guys.
Okay, we're under 4 minutes. We're coming up on the Christmas vacation. I'm not sure that we should meet probably until next year. Does that sound reasonable to everybody? At least that's my plan. And so I guess there'll be a meeting next Sunday.
Next Sunday?
Yeah, because that's before Christmas, right?
Okay. Okay. Because we're scheduled to have a Zoom call next Saturday. And then the next one will be on the 4th of January.
Aren't you presenting on Saturday? Next Saturday, you're presenting.
Yes.
And Ian will present on Saturday morning, and then I guess we'll have a cosmology group meeting on Sunday, the following Sunday, and then the next won't be until January, until after New Year's. Does that sound?
Mm-hmm.
Okay.
That's fine.
All right. And I want to wish everybody a Merry Christmas. It was a little bit early, I guess, for that.
Well, Merry same to you.
You have an official Merry Christmas from Saint Nick.
Yeah. Well, I'm sorry, I can't speak. I have a stuttering problem. I apologize for it. I can't speak. I would say that I would love to speak with anyone through email or Zoom calls or Skype or however at any point throughout. I'm highly interested in all of this. So, okay.
All right. I think that we also have two people here who haven't spoken, Kasim and Robert. Robert doesn't have his mic on, but I guess they're listening. And I just want to welcome because I don't know that we've had them with us before. And so you're welcome to participate. And thank you for coming by. All right, we got two, excuse me?
Ho, ho, ho.
It does look like I was mistaken. I do think that there is a recording of the second session. I looked in the file and it looks like it's in the file, and hopefully this session will be recorded as well. And I guess Nick, you'd be interested in editing or doing something with that. I know Roger requested that he be allowed to have the recordings. I don't know that there's any objection to that. Roger Anderton.
But Roger has been putting them up on YouTube. So unless that's done, I think, Harry, they're sort of lost, are they, in the ether somewhere?
Yeah, I thought Nick was going to do that.
Well, the second thing, no, David was writing about some program called, Redirect or something like that. StreamYard put him up on YouTube directly. Zoom doesn't have that mechanism. I don't know who David was expecting to take Zoom and put them up there. I guess I can do it, so I'll take a look into it.
Well, I see why David has some issues with Zoom and using Zoom, but I think it's easier for more people to participate with Zoom than it is with StreamYard, and I think that's the issue that people are kind of objecting to, other than the fact that I think it's easier to use Zoom than StreamYard.
Yeah, I can hear you much better on Zoom, Harry, than on StreamYard.
Oh, yeah, no problems.
I think it's certainly more suitable for an interactive discussion, an informal interactive discussion, where you can